Support for this podcast comes from Addition Financial, offering their Savings Plus account with a 4% annual percentage yield, serving Central Floridians since 1937 and was recently named one of Newsweek's best regional credit unions. More at additionfi.com/NPR. Applicable on savings up to $5,000. Rate subject to change. Federally insured by NCUA.
Sun science during a solar eclipse. You're listening to Are We There Yet? The radio show exploring space exploration. Hi, I'm Brendan Byrne. A total solar eclipse will shade parts of the Earth in darkness on April 8th, and scientists and viewers are gearing up to take a closer look at the skies during this rare phenomenon. Only some of the U.S. will be in the path of totality, ranging from Texas to Maine, but Central Floridians can expect more shade than normal. We'll speak with astronomer Terry Oswald about the ways to view this eclipse. Then, how are scientists taking advantage of this celestial event? Researchers at Embry-Riddle Aeronautical University are using the solar eclipse to launch rockets into the sky. We'll speak with Eero Bhajatia, a professor at Embry-Riddle, working on this launch. That's ahead on Are We There Yet? This solar eclipse is rare and exciting, and millions of people around the country will be able to see the effects from this celestial phenomenon. But how should you view this eclipse, and why is it so special? Well, here to answer those questions is Terry Oswald, an astronomer and the Associate Dean of the Physical Sciences Department at Embry-Riddle Aeronautical University. Terry, welcome back to the show.
Thank you. Good to be here.
Terry, it always seems like we have something exciting to talk about in the world of astronomy when you're on the show, and today is no different because we've got an eclipse coming up. What can we expect from this eclipse?
Well, here in the Central Florida area, we'll probably not notice much happening. The sun will get dimmed by something like a factor of 58 or 60%, depending on your exact location. And that's not as much dimming as a mildly cloudy day. So you really ought to, if you can, travel to one of the areas that are in the path of totality, because that is a once-in-a-lifetime experience. I'm going. So the thing that you might notice, even if you're not an eclipse aficionado, is that shadows underneath trees look a little different. All the little dabblings of sunlight that you see under a tree or under fences that have holes in them form little pinhole images of the sun. So those little spots of light all over the sidewalk as you're walking down the street through the trees are actually little fuzzy pinholes of the sun. During this partial eclipse here, you will see that those little pinhole images of the sun are present. So, weird-looking little shadow, and that's probably about the most people would notice if they don't know in advance.
Can you explain the physics behind an eclipse? What is actually happening in our celestial neighborhood to actually make this phenomenon occur?
Imagine one circle. Now draw a circle on top of that circle, and now tip one of those circles a little bit, say 5 degrees. You can imagine that those two circles only intersect in two places when they're not lined perfectly up. Those represent the plane of the Earth's orbit around the sun and the plane of the moon's orbit around the Earth. Now, throw the sun in the way. In order to have an eclipse of the sun, the moon has to be directly between the Earth and the sun so that we are in the moon's shadow. That can only happen if several things happen simultaneously, and that is the moon is in the plane of the Earth's orbit, one of those two intersection points, and perfectly lined up with the sun at that point. The shadow is so small that you have to be in a particular spot on the surface of Earth in order to be in that tiny little shadow. Plus, it's moving at about 1,100 miles an hour. So you will only get a few minutes at most of darkness. This is kind of a unique attribute, maybe unlike anywhere else in the galaxy for all we know, because the moon is about 400 times smaller than the sun, but it's also about 400 times closer to us than the sun is. And so it looks in the sky to be almost exactly the same size as the sun, even though they're vastly different in real size and real distance. And that means that eclipses are rare, relatively rare, and spectacular.
Terry, you said you're traveling into the path of totality. Where are you going to be, and what can you expect to see there that will be a little bit different than, let's say our Central Florida listeners here?
I've only seen one total solar eclipse in my life when I was very young, and I am determined to see more. And so I'm traveling up to Indiana, and Indianapolis happens to be one of the major cities that is almost directly in the line of the total eclipse. What will happen is that the times here in Central Florida are not that much different than they are up in Indiana. Here in the Orlando, Central Florida area, the eclipse starts at about 1:47 in the afternoon on April 8th, and it ends several hours later at about 4:17. But it never gets to be total. Only about 58% of the sun's area is covered up, so the sun will be dimmed by about 58%. So, like I said, you won't notice much is happening unless you know in advance. And I'm obliged to say, never ever look at the sun without proper eye protection.
What is the proper way to look at this?
Talk to your local astronomer and or log into the American Astronomical Society's website and look at what the vendors that are selling safe observing gear are. There's still time. You might have to pay for express delivery, but
Terry, there's also, just outside of the awe of a eclipse like this, there's also some scientific interest, right? What will astronomers be looking at for this kind of rare celestial event that is happening?
It's grown over the last few decades to be less scientifically important because we have spacecraft that can directly view the sun at all times. But I don't want to downplay the dramatic aspects of this. There's still quite a bit to be seen. And for example, we're nearing the solar maximum in its activity cycle. There are spots on the sun right now, even as we speak, that are big enough to be seen with the protected eye and no magnification. So if you've got your little solar sunglasses and you know they're safe, approved safety, you can look at the sun and probably see a spot group right now that's generated several outbursts over the last few days and aurora in the higher latitudes. The eclipse itself is scientifically important in that it gives us a real-time glimpse of the outermost atmosphere of the sun that is simply too faint and lost in the glare of the disk of the sun. Disk that you see in the sky is called by astronomers the photosphere, which literally means ball of light. And when that is covered up by the moon, you can see around the edge the upper atmosphere of the sun. The pinkish rim around the eclipsed sun is known as the chromosphere, ball of color. And above that, if the weather conditions are sufficient, one could be able to see the corona, which is the outermost atmosphere of the sun. It's a pearly white, very faint, and very stringy or rayed-looking structure, and we're in that. The whole solar system is in the sun's outermost atmosphere. And so we like to see that because for the few minutes that totality exists, you can take direct measurements of the light and its distribution across wavelengths and compare the structure that one sees at the limb or edge of the sun, at the moon's edge, to what models predict. 1919 was a banner year. There was a solar eclipse that was visible from South America and the western coast of Africa that observations of the sun were used to prove or at least confirm one prediction of Einstein's theory of general relativity, that gravity can bend light. That expedition, there were two, one to Brazil and one to an island off the coast of Africa, showed that pictures taken of the eclipsed sun, which brought up stars in the area around the sun, compared to pictures taken of that same place in the sky a few months later when the sun was in another part of the sky, showed that the stars looked like they had been displaced outwards away from the sun by a teeny bit, but it was a teeny bit predicted by general relativity.
Fascinating. All from those astronomical observations. That's really incredible. Finally, Terry, you mentioned this earlier in our conversation that this is the phenomenon of the eclipse is unique to is rather unique and rare to our planet and moon system here. But I'm recalling a few years back, you and I had the chance to fly aboard Sophia, which is an airborne observatory, and scientists were looking at an eclipse on another planet, right? An occultation of another moon and planet. Can you briefly recap what we saw and how this does happen kind of elsewhere in our solar system, albeit you need to have a very specialized telescope to to observe it?
And that particular event was that you referred to with the Sophia mission was a case where a star, much more distant than any planet in the solar system, was occulted by one of the moons of Neptune, a big moon named Triton. And Triton has an atmosphere. As the planet satellite, Triton passed in front of that background star. You can imagine a tiny little shadow of starlight, the star's shadow. Sophia was flown out to the middle of the Atlantic Ocean to be in that shadow line. The importance of that was that the starlight didn't wink out as the Triton covered it up, and it didn't instantly wink back in as the planet uncovered it, because it has an atmosphere. So the dimming was gradual and the brightening was gradual. In the exact way that the light dimmed and then came back is a probe of the atmosphere of the moon, Triton. The moon doesn't have an atmosphere. So in that case, what you will see in a sequence of events will be gradual dimming. Those of you that have clear horizons and are in the path of totality will see the shadow approaching. You will see what looks like a weird shade coming towards you. As second contact occurs, the moon has just barely covered up the sun, and you can probably see what are known as Bailey's beads, little peaks of sunlight flooding through the valleys on the edge of the moon for a few moments until they're completely covered up. It's at that point when the last little bead of sunlight disappears and totality begins that you could take those protective glasses off during those 3 to 5 minutes that the totality lasts. But the second the Bailey's beads come back on the other side of the moon's limb or edge, it's time to put the glasses back on. Please don't leave those glasses on during totality or you'll really miss the biggest part of the show. That's a mistake some beginners make, is that they've been told so much to never look at the sun that they keep them on during the actual totality when there's no bright points of light. That's the really fantastic time. You'll see the corona, you'll see the chromosphere. Night will come, you'll see in the sky around the sun right now, off to the right, you'll see Saturn and Mars and Venus. And off to the left of the sun, you'll see Jupiter. And maybe if it's bright enough, there happens to be a comet in that general part of the sky that might be bright enough to be seen with the naked eye while the sun is eclipsed.
Well, I am super excited that you will be traveling there, and I cannot wait to hear about your experience and hopefully see some of those images. Terry, thanks again for bringing us up to speed on the latest happenings in our universe. Thanks, Terry.
Thank you for inviting me.
Still to come, launching rockets during an eclipse for science. That's ahead on Are We There Yet?
Support for this podcast comes from Addition Financial, offering their Savings Plus account with a 4% annual percentage yield, serving Central Floridians since 1937, and was recently named one of Newsweek's best regional credit unions. More at additionfi.com/NPR. Applicable on savings up to $5,000. Rate subject to change. Federally insured by NCUA.
You're listening to Are We There Yet? I'm Brendan Byrne. While viewers are looking up at the skies, scientists and researchers are using the eclipse to their advantage by conducting experiments, including rockets into the sky. NASA's teamed up with researchers from Embry-Riddle Aeronautical University to launch 3 sounding rockets before, during, and after the eclipse to test how it might interfere with communications here on the ground, like GPS and satellites. The mission is led by Aero Bhajatia, a professor of engineering physics at Embry-Riddle Aeronautical University. He joins us now to talk about the mission and what his team will do during this sun's blackout. Ara, welcome to the show.
Thanks, Brendan.
So you and your team are going to fire a rocket at a solar eclipse. I assume it's not because you have a vendetta against the moon or the sun, but is for scientific purposes. Why are you launching a rocket at this particular moment in time?
Earth's atmosphere has many layers, and one of the layers is the ionosphere, which roughly starts at 60 miles or so and goes up to about 300 miles. That is the densest part of it. And all our radio communications to the satellites go through this layer, as well as many over-the-horizon radar signals, ham radio signals kind of bounce off of it. So any signal that is going through it or reflecting it or refracting through it is dependent upon what are the conditions in the ionosphere. And the ionosphere is disturbed by a variety of events, solar geomagnetic storms, you've got aurora, you've got volcano eruptions, you've got thunderstorms that create disturbance there. And all of these leads to basic physical process, basic physics. Now, if you're trying to understand the ionosphere disturbances from these natural phenomena, you could be waiting for a long time because sometimes you have thunderstorms, sometimes you don't. You don't know when the volcano is going to erupt, You can have a little bit of a advanced guidance of when the solar storm is going to hit, but not much. And a lot of these basic processes that happen are also what happen under an eclipse. But the beauty of eclipse is that you know exactly when it is going to happen, where it is going to happen, and what time to shoot, rockets at it. So it's a perfect scientific experiment setup. Plus, it also really helps us understand that this eclipse, which goes, twice a year is what we end up having for the solar ones, what type of disturbances it could create. Ground-based observations clearly show us the large-scale effect. And they do create radio communication disturbances. But the smallest scale perturbations also create disturbances. And those things, tens of meter scale, are very hard to see by ground-based observations. Therefore, the only way to look at them, especially from 60 miles to 260 miles, is through rockets. Let's talk about a few of these different things. So the most common one that people do worry about are GPS signals, right? So GPS satellites are at 22,000 kilometers and their signals are coming down. And you need a lock on those signals to be able to figure out your 3-dimensional position, latitude, longitude, altitude, as well as time. Now, in order to find those 4 variables, you need access to only 4 satellites. Now, at any point in time, at low latitudes or mid latitudes, you have more than 10 satellites visible. It is not that GPS will stop working, but the signal deteriorates, and we are then relying upon at least 4 satellites being visible. So you could have a disturbance, let's say this part in sky, so maybe one satellite is disturbed, maybe another one. But as long as you have 4, could you get unlucky where more than 6 or 7 satellite signals get disturbed? Then your position lock is not very accurate. So that is one thing we worry about, to make sure our positioning is good, because we are now more and more dependent upon GPS type signals. The other thing is military and even other folks are very interested in over the horizon radar. So where eyes cannot see and you're trying to bounce the signal off of the ionosphere, trying to look at things which are over the horizon. So now your refracting mirror is this ionosphere. So every time you have disturbance in that, now you don't know where your over the horizon radar is going. So that gets disturbed. You also have other kinds, ham radio operators. It's a two-edged thing. You can also use the ham radio operators to study the ionosphere. But when you're actually trying to use ham radio for communication, well, then the ionosphere can come and disturb you. So we're using both, and there are other peers in the community who are using ham radio networks to actually help study the eclipse. And the effective eclipse on ham radio operation. And then there are, of course, some other radars, which are just space weather radars, meteorological radars. Their signals get disturbed. And so the ultimate goal is to be able to study the ionosphere at every possible scale so we can start modeling it better and therefore predicting that, hey, something like this is going to happen in the ionosphere. So all these signals are going to get disrupted. So let's be prepared for it and let's not worry about.
So really important implications with kind of real world applications. So I'm glad you're doing this. But let's talk about the process of actually firing a rocket into the eclipse. I still can't get over that. That sounds like the coolest job in the world. Tell me a bit about the actual process itself. So where is this rocket launching from? What does it look like? And what kind of instruments are on board to uncover some of these things that you've outlined in our conversation?
I should remind your viewers also that we launched these 3 rockets during the annular eclipse from White Sands Missile Range in October of 2023. And because it's a missile range on the land, we recovered them, we refurbished them, and we are now launching them again from the Wallops Flight Facility, and now we will lose them in the ocean. I would also like the listeners to visualize one thing. Imagine a pond or a lake which has a little bit of ripples all on it, just like a normal day. And now imagine a very strong and big motorboat just racing across the pond. And it's going to create first an immediate bow shock, sort of a wave right around the boat. But then those waves are going to ripple and kind of go all across the pond, as you go far. So the Eclipse rockets that we did, what we did was we launched them kind of towards the path of annularity. Imagine launching them closer to the boat to study the phenomena closer to the path of annularity. Now, for the Wallops launches, we are launching them away from the path of totality to see how the waves continue to keep on expanding and if they create small-scale disturbances. Because remember, these waves are going to go for hundreds of kilometers and thousands of kilometers. So I don't have to be directly underneath the totality. I can be anywhere close to it. A lot of ground-based observations in the past have shown that as the eclipse is going by, you are seeing a sunset and then you are seeing a sunrise. And so our objective is to launch 3 rockets, one a little bit before the local peak eclipse, right? Wherever we are, in this case at Wallops, there is a certain point in the day when we will see maximum solar occultation for that location. So we will launch one rocket 45 minutes before the local peak eclipse, one rocket at the local peak eclipse, and the third rocket about 45 minutes after the local peak eclipse. So we will be able to see, again, as the boat is kind of going by, we will see a little bit how the pond was slightly before the boat went by, then right when the boat went by, and then how are the ripples after the boat has kind of gone by.
You're seeing different aspects of the disturbances, but also building upon previous knowledge from your last launch. Okay,
exactly. So the name of the mission is APEP, and people think of it as only one, but no, it's actually the whole science investigation is a 6 rocket investigation. 3 very close to the path in the October annular eclipse, and now 3 a bit farther away from the path from the Wallops Flight Facility in the total eclipse.
So as you mentioned, this is not the first type of investigation like this. You launched during one of the more recent eclipses. What have you learned from that preliminary data?
Yes, so we launched the same 3 rockets from the October in the October 2023 eclipse, one before the peak eclipse, one at peak eclipse, one after. What we saw was that the rocket that was launched before the peak eclipse did not see any small-scale perturbations from like 100 kilometer to the 300 kilometer altitude. But the second rocket at the peak eclipse and the third rocket not only saw those small fluctuations, but also saw them grow as if the froth was increasing. We are launching 3 rockets, but each rocket also throws out 4 sub-payloads, each one of these also capable of measuring plasma density, magnetic field. So we launched 3 rockets, but the data profiles are equal to 15 rockets. And all these independent bodies saw the same thing, which increases the confidence in the data that we are collecting. We are hoping to see some similar cool small-scale phenomena in these upcoming launches.
Eric, let's talk a bit about your team. I know that you're leading this team, but there are also a lot of Embry-Riddle researchers and even students that are partaking in this research. Tell me a bit about how that all works out and the kind of experience these young researchers are getting developing this technology and working on this scientific investigation. It's got to be awesome.
How this mission started was we were digging ourselves out of COVID, and I was sitting with my postdoc at that point in time, but now my colleague and a research scientist, Dr. Shantanath Chaudhary, and we were figuring out, hey, what kind of new proposals do we need to write, especially with rockets? And then we realized that lo and behold, both of these eclipses that are happening within roughly about 6 months of each other were perfectly positioned with existing sounding rocket ranges that NASA had. And so it was just like a moment of voila, like, hey, this is the perfect experiment. And we already were building a series of rockets for NASA. There is a sporadic electrodynamics rocket that we were building and another one that we called a Speed Demon, which was a demonstration mission. And so the instruments were all lined up and they were perfect for studying electrodynamics, neutral dynamics. And so we just wrote a NASA proposal saying, hey, instruments are ready, the rocket designs are ready. Let's just launch this and we can save money by recovering the three. Now, when you talk about students, one of the master's thesis defense that I just finished, as I was telling you before, is a story of a student, Josh Milford, who's been working in my lab since he was a freshman, sophomore, and at an engineering physics program that we have. So he's been working with magnetometers to study what kind of currents in the atmosphere can get set up due to solar events, due to geomagnetic activities, and how to measure those magnetic fields. And so all these rockets are equipped with sensors to measure plasma density, plasma temperature, electric fields, magnetic fields, neutral density, and we are hoping even neutral winds. And every single instrument is designed by undergraduate students, master's students, PhD students. So these students not only get to build the instruments, but actually fly them and then also analyze the data. So for example, Josh, who's been working with me since his freshman, sophomore year, has now launched instruments on 5 rockets and 3 CubeSats, and they're all working. And now he still has stuff going on another 6 more rockets. Now, he would have graduated, but all his fingerprints and oils will be actually cleaned them. But his stuff is going to continue to fly. And I'm just naming him, but there's a whole bunch of others with Rachel Conway, Henry Valentine, Nathan Graves, lots of great students.
Well, Ira, I know you have a lot to get done before launch day, so I will let you go. Best of luck to you and your team. And I hope to have you back on to discuss the findings of this next launch.
Absolutely. Thanks, Brendan.
That's going to do it for this week's show. No matter where you watch this eclipse, please do it safely. If you're not already, be sure to subscribe to the show's podcast feed so you never miss an episode. Do that on Apple Podcasts, Spotify, YouTube, or wherever you get your podcasts. We got more space coverage online. Visit WMFE.org/space. Are We There Yet is a production of 90.7 WMFE News. Our producer is Marion Summerall. Our intern is Emily Ching. Editorial guidance from Latoya Dennis. Support for Are We There Yet comes from our listeners. Until next week, I'm Brendan Byrne. Thanks for listening.